New data modeling patterns have solved one of the most vexing problems of data warehousing and business intelligence: how to get application development started quickly and still not suffer from any oversights made during requirements gathering or during the design of the database schema. In this screencast, Ceregenics Chief Systems Architect, Ralph Hughes, will introduce you to the first of two hypermodeling techniques that will empower your development teams to design and deliver new business insights in a fraction of the time that traditional Inman or Kimball data modeling patterns require. But first, let's hear a little bit about our presenter.
I'm Ralph Hughes. I help companies leapfrog their competition by using data and information to rapidly define new products, cut costs, and achieve better customer outcomes. I work with Ceregenics, a U.S. consulting firm specializing in data warehousing, business intelligence, and big data analytics. Perhaps you've attended one of my classes at the DAMA or TDWI conferences, or read one of my books that explain how to achieve speed through fast requirements, fast programming, and automated testing. I've taken the best practices from software engineering, agile development methods, and advanced productivity tools and combined them into a method called Agile Data Warehousing. This method allows you to build new information systems with 2/3 less labor using tools that accelerate implementations by another factor of 3. To thrive in the global marketplace today, your company will need to rapidly assemble and expand its infrastructure for big data and business intelligence. You're going to need the acceleration that Agile Data Warehousing can give you. Many people think that all you need for Agile development is to find a Scrum Master and have them start conducting sprints of team-based programming. However, business intelligence and big data applications are just too complex for plain vanilla Scrum or Kanban. We had to invent instead a highly disciplined incremental development method called Agile Data Warehousing. Over the past 15 years, we've created and evolved a wide range of techniques so that now our set of best practices covers the full range of software engineering disciplines, such as requirements, project phasing, database design, quality assurance, and program management. In this screencast, we will focus upon the best practices in the area of database design. It used to be that data warehousing teams had to decide at the start of a project whether they were going to use a third normal form data model or a set of conformed dimensions. Today, we have two other data modeling approaches to choose from, approaches that are agile and will free us from having to do a big design up front and let us adapt an existing warehouse when new requirements come along. Hyper-Normalized data models focus upon the integration layer of a data warehouse and only the integration layer, but they make it very easy to build an enterprise data warehouse in an agile fashion. We can start small with just a few tables and then evolve our integration layer as needed. In contrast, hyper-generalized data models not only make the integration layer fast to build, but they also allow us to computer-generate the warehouse's presentation and semantic layers as well. Compared to the standard normal or the conformed dimensional forms, the two hyper-modeling paradigms enable data warehousing teams to deliver BI applications faster, better, and cheaper. In this screencast, we will focus upon the hyper-normalization technique, which will make the hyper-generalized approach easier to understand when we cover it in a future video. Why do we need new hyper-modeling techniques? The old data modeling styles are just too unresponsive for the current business climate. They demand we spend months drafting a data model before we can start coding an application. They also force us into extensive data conversions whenever we have to change the tables of an existing warehouse. The foreign keys that implement the one-to-many relationships between tables are the primary weakness in these models. In this diagram, we show a model for a small data warehouse of sales transaction, which is in third normal form. We can see that it involves a high number of one-to-many relationships between the tables. If we focus upon the relationship between the vendor and product tables in particular, we can see that any vendor can provide multiple products, but every product belongs to just one vendor. To support this relationship, the developers must put a foreign key in the product table that will declare the parent vendor for each product record. Now say the business requirements change, forcing us to add a table for purchase contracts. Every product record will now have two parents, a vendor and a contract. To support this requirement for a data warehouse already in production, the team will need to not only add a new foreign key to the product table, but they must go back and convert the product records that already exist to give them a value pointing to their new parent records in the contract table. This update will require a data conversion script. Data conversion scripts are programs in and of themselves. They demand that the team undertake steps for requirements, design, programming, validation, execution, and quality control. Yet because each conversion script is used only once, it amounts to throwaway programming. This makes data conversions very time-consuming and very expensive. They undermine the agility of a data warehousing team. Let me show you what the data model between vendor and product would look like if we were to hyper-normalize it. First, we take the business identifiers for both these objects and send them to their own special purpose tables. BK vendor and BK product now have just the business key values and a surrogate key for linking purposes. We also add some metadata columns such as load date. Our second action is to create a linking table between these two business key objects in order to record the relationship between their records. Note that we model this link as a many-to-many relationship, even though the records we'll put in there will manifest only the one-to-many link between vendor and product, respectively. Note also that this linking table holds only the surrogate keys for the two objects it joins, plus some metadata columns. As a final step, we send all the remaining attributes of the original tables to their own dedicated attribute tables, A_vendor and A_product. This is called ensemble modeling, where you model objects using multiple special purpose tables and then must remember when working with them that it takes records from an ensemble of tables to portray any given object. It may seem overly complicated at first, but in a few slides I will show you that ensemble modeling provides a big advantage for making data warehousing faster, better, and cheaper. To see these advantages, we'll have to hyper-normalize an entire model. Our sales data warehouse, for example, starts with 7 tables. In step 1, we decide which starting tables represent the business objects that our company wants to track, and we prepare to create business key tables for them. Here, 6 of the tables have been colored green, meaning that we will soon transform them so that they contain only the business key values that identifies each instance of the objects they describe, plus a surrogate key and metadata columns. Note that order detail has been left gray because the modeler here decided that it should be treated just as a link between order header and product rather than as a separate business object on its own. In step 2, we add the linking tables between the business key tables, coloring them yellow in this diagram. Note how order detail is now a many-to-many link between order header and product. In step 3, we send the attributes to the blue attribute tables, including those attributes for the order detail linking table. Our starting model was in third normal form and it had 7 tables. After applying ensemble modeling concepts that relegated columns to tables specially designed to hold either business key, linking, or attribute information, we have 18 tables. Far more tables than a normalized model contains. That's why I call this process hyper-normalization. In the old data warehousing paradigm, each data table required its own ETL routine. So, having watched the hyper-normalization of an entire model, you may be thinking, geez, hyper-normalization has created far more tables, so it must be also creating far more work for the ETL programmer. What a crazy idea. But this is where we need to observe a crucial aspect of ensemble modeling. Consider all the green business key tables. They all have the same structure, a business key value, a surrogate key, and some metadata columns. Why should we program a separate ETL module for each green table here? Why not create instead a parameter-driven data transform that we can call repeatedly from a driver script? All we have to do is say, "Dear ETL module, here's the source table I want you to warehouse. There's the target business key table I want you to load. And here's the column or columns that hold the business key values. Please shoot through this source table, and anytime you find a business key value not already in the target table, add it and add also a surrogate key and a few other pieces of metadata." So for the green business key tables in this diagram, we need to program only one green ETL module and boom. We can load all the business key tables by making repeated calls to that module and varying the parameters that we give it. Same idea works for the yellow linking tables. They just hold surrogate keys and metadata values. So why not program a yellow ETL module for loading all of them? The attribute tables are a little trickier. That reusable module will need parameters so that we can say, here's the source table, there's the target table, and here's the columns I've already used for business key and linking tables. Take all the other columns you find in the source table, and every time you see a unique combination of values among them, send those values to the target attribute table. You should find an appropriately named column in the target table for each column you have in the source. So look at what we've accomplished with ensemble modeling here. Yes, we have more tables than in a third normal form repository, but as soon as we program just 3 parameter-driven ETL modules, we're ready to load the entire integration layer for our data warehouse. Hyper-normalization with reusable ETL routines allows teams to stand up a data warehouse in 1/5 the time as a traditional Inman or Kimball data model. Hyper-normalized data models also allow you to easily adapt a data warehouse, even once it has been loaded with billions of records. Take the submodel from our example that holds the vendor and product information. Earlier we saw that when the business requirements demanded we add a purchase contract entity, the third normal form model required us to undertake some costly redesign and data conversion. Not so with the hyper-normalized data warehouse. Here we need to add only tables for the purchase contract and linking tables that associate it with vendor and product. We then simply add calls to our green, yellow, and blue ETL modules to load the new records into the new table. Because all the foreign keys have been relegated to their own special purpose linking tables, there is zero impact upon the vendor and product tables. Evolving the data warehouse required only adding tables and inserting records, no data conversions. That's where the agility comes from. We can now start our warehouses small, add on tables as we get new requirements without risking that the design or the data we've already acquired will somehow be broken. The risk implicit in this data warehousing project has now nearly disappeared. Now, of course, there's no such thing as a free lunch. So what price do we pay for all this flexibility? What people usually say is that it's very easy to get data into a hyper-normalized warehouse, but then it is all that much harder to get data out. There's 2 reasons why they say this, both revolving around the attribute tables. First, the load date column in an attribute table allows the warehouse to accumulate many attribute records for a given parent record in a business key or linking table. As the warehouse tracks the changing business reality for an object, the attribute table could end up with hundreds of related records for it. To retrieve from the warehouse the business situation for a particular point in time, you'd have to query for just the right attribute record that pertains to that point in time and ignore the rest. The SQL for such a query requires a correlated subquery, which can get pretty tricky to write. Second, Agile data warehousing practitioners tend to group information columns into separate attribute tables based upon whether they change daily, weekly, or monthly. Attributes originating from different upstream systems are also relegated to separate tables depending upon their source application. With so many different attribute tables linked to a given parent table, you might have some attribute tables without a record for a given business key or linking record, a fact which will cause that record to be dropped from a query unless you use some type of outer join. So with more tables that need to be queried using outer joins and correlated subqueries, the SQL to retrieve data from a hyper-normalized data warehouse can become very complex to write indeed. We Agile data warehousing practitioners have devised some workarounds for such as seeding tables with null records for a given point in time, or pre-joining business objects to create point-in-time tables or bridging tables, but even with these techniques, retrieving data from a hyper-normalized data warehouse is not easy. Does all this additional complexity for writing retrieval queries matter that much? For the most part, no. All this ensemble modeling is focused entirely upon creating integration layers, not the presentation or semantic layers that the end users interact with. Keep in mind that hyper-normalization and the reusable ETL modules allow us simply to create, populate, and evolve a persistent staging layer that performs light data integration. I call it a persistent staging layer because we're just layering snapshot after snapshot of the source systems into the integration layer tables without adding any derived columns aside from metadata. So we're just staging the data for later projection into the presentation layer star schemas. I say light integration because yes, we do capture everything that looks like a customer in all those sources, and we put them into a shared customer business key table. But we're not standardizing or coalescing source data into fancy concepts such as party that can play multiple roles in a given transaction later when we do our analysis. That said, the fact that we need to create only 3 reusable ETL routines and we can then begin storing away all the information pouring in from the source systems is an impressive accomplishment, especially when you consider that we can build out the data warehouse a slice at a time and adapt easily to new business requirements. There are many styles of hypernormalization to choose from. What I've shown in this screencast is a style called data vaulting that was invented and popularized by some Americans starting nearly 15 years ago. Shortly after data vaulting was introduced, data warehousing professionals in the Netherlands began using and evolving those concepts, and they now have a vibrant open source approach to ensemble modeling and programming that has become widespread in Northern Europe. On a separate track, the Swedes got inspired by six-normal form, also known as temporal modeling, and took ensemble modeling to a new extreme. They invented anchor modeling and even set up a website where you can computer generate the schema, load routines, and retrieval queries you'll need to build and operate a data warehouse. Recently, the Americans moved on to publish a Data Vault 2.0 standard, whereas the Dutch began merging the old Data Vault ideas with anchor modeling to create a third major approach called unified anchor modeling. Just in case you were wondering, here's a look at an anchor model generated by the Swedes' web engine for a very small data warehouse. The biggest difference is that anchor models create a new table for every attribute associated with a business key or linking table. As you can imagine, this practice leads to many more tables than a data vault would have, but on the upside, it lends itself more to pattern-based programming for loading and retrieving data. Though hypernormalization offers many advantages, in fact so many that data warehousing professionals cannot afford to ignore it, the practice and its many styles do raise some crucial questions that Agile data warehousing teams need to answer. These questions include, which flavor of hypernormalization would be best for my particular use case? What does the physical model for a hypernormalized data schema look like? What are the best platforms for hypernormalized schemas, especially when you consider performance? How do we incorporate data governance objects in a hypernormalized data model? Where should we place columns that are going to hold derived columns that are the result of applied business rules? How should we merge a hypernormalized schema in with a third normal form enterprise data warehouse that already exists? Can a hypernormalized warehouse support self-service BI? And finally, how do the advantages for hypernormalization compare to those of hypergeneralization? Ceregenics is specialized in Agile data warehousing, and we're big advocates of both hypernormalization and hypergeneralization. We understand the use cases that will determine which paradigm and which style within a paradigm is right for you. We provide experts to work alongside you as you undertake your next big data, business intelligence, or enterprise data warehousing project. We will collaborate with you on project definition, solutions planning, architecture, data modeling. We can provide Scrum Masters, automated test engines, or quality assurance planning. We can guide you to selecting the best productivity tools for an Agile data warehousing program, and we can advise you on how to arrange program management for situations where many Agile data warehousing projects must be organized into a single effort.
In this screencast, Ceregenics Chief Systems Architect Ralph Hughes introduced the notion of hypermodeling and explored hypernormalization in particular. We saw that hypernormalization trades complexity in some areas for the ability to rapidly create, populate, and evolve a data warehouse using only a few parameter-driven ETL modules. You can learn more about Agile methods for data warehousing, business intelligence, and big data analytics at Ceregenics' website. You can also search the internet to locate our other videos on Agile Data Warehousing. Contact us if you need a fast start on a new project or a turnaround for an ongoing development effort. And good luck with your projects.